Right. So it's the second presentation of this morning. We've got
Attribution is in the object.
Attribution is the object,
Yeah.
and we've got two guys from Proofpoint and Anomali to hopefully entertain us and tell us loads of stuff we don't know. Please go ahead.
Yeah. Thank you. Good morning, everybody. Thank you for coming to our session. So we are going to speak today about RTF attribution. I know attribution is a very sexy word, but with very bad repetition. I mean, like, we security researchers like doing attribution, threat analysts and reporters like asking about it, but usually it's very tricky and it usually fires back. Fortunately, we are only going to focus on technical attribution, trying our best today to avoid getting into the muddy water of attribution. My name is Ghareeb Saad. I'm a threat intelligence manager at Anomali.
My name is Michael Raggi. I am a senior threat research engineer at Proofpoint. So we found this quote, which we thought especially relevant to this presentation. Nothing made by a human can avoid personal expression. We find this to be especially true in cyber threat research. When threat adversaries attempt to obfuscate their fingerprints, there is more and more that ends up pointing back to them, whether it be shared strings, PDB paths, code bases. This presentation is seeking to identify the human fingerprints in the tools that threat actors build to target our organizations. So attribution in the object using RTF object dimensions to track APT phishing weaponizers is going to start by defining what a document phishing weaponizer is. We're going to explain why we need to track these weaponizers. We're going to dig deep on the RTF file format and RTF weaponizers particularly. And then we're going to discuss 4 attribution techniques for RTF phishing files. And then finally, we're going to end up with an APT case study on the Royal Road RTF weaponizer that was used by both Chinese and then Indian APTs for a very brief period of time. So let's dive in. What is a document phishing weaponizer? Well, a document weaponizer is a tool used by threat actors to create a malicious document from a pre-existing phishing lore utilizing a code to inject malicious exploits into a document to exploit a vulnerability or a zero-day. So this is a distinct tool, a script, from the actual exploits or vulnerabilities that are going to be exploited by the document. And they're often things like a Python script. And the reason that threat actors are utilizing a weaponizer is to make their operations more convenient as well as scale them. So they have the ability to utilize a script disseminated across their operators, allowing them to scale operations and customize phishing lures across campaigns while automating the injection of malicious payload exploits into Word documents. So let's visualize that. Every campaign begins with a threat actor assembling a plausible social engineering lore. They then create a lore document utilizing a word processor or software on their host. Next, they're going to run the weaponizer script, which will inject the malicious code into the Word document, resulting in a weaponized document. So this is now a document capable of exploiting a vulnerability or a zero-day. And then finally, that document can be attached to an email and delivered to a victim at one of our organizations. And to help visualize what these weaponizers look like, these are 2 different scripts for equation editor exploits that actually inject these CVE exploits into RTF files. Okay, so now that we know what they are, why should we track them? Year after year, reports come out that continue to cite phishing as a top malware infection vector, including attachments. That's not surprising. A lot of these attachments are built by phishing weaponizers. When you start tracking phishing weaponizers in your environment, you gain visibility that you didn't have previously. It gives you the ability to attribute phishing attacks to known sophisticated and unsophisticated actors based on shared weaponizers. The same principle holds true for identifying new payloads using shared weaponizers. You can even track objectives and targeting across multiple campaigns if you have that visibility. And then finally, we're going to demonstrate today that the most extreme use case is identifying new exploits entering the wild through known phishing weaponizers.
Perfect. So why are we focusing today on RTF attribution and tracking? So as Michael just said, like, it's very important and useful to be able to track and attribute exploits in general. not only for security researchers, but also for threat analysts who is trying to understand attacks and exploits targeting his organization, trying to group it and attribute it to a certain actor or previously seen incidents. And since RTF is one of the most common used file format to deliver exploits, I would say if we exclude macros, which is technically not exploits, RTF are currently the most commonly used format or file format in phishing attachments. I mean, on a daily basis, on our threat hunting and APT tracking, we see a lot of malicious RTF files, and we are always trying to attribute it to a certain actor. And we thought that might be a very good idea to combine or group all the techniques and methods we are using to track and attribute these RTF weaponizers and release a research paper summarizing our findings. Only this year, we have been tracking at least 22 unique RTF weaponizers used by multiple actors, exploiting at least 6 different CVEs numbers. So we are hoping in the next slides, we will be summarizing the techniques and the tools we are using to track and attribute these RTF files. Just to start with a quick summary of rich text format. Rich text format was developed by Microsoft in 1987 with the goal to achieve cross-platform document interchange. And to be able to achieve this goal, RTF specification was created to be very flexible. And that led to one important thing, which is when you create a very flexible specification, you have very complex parsers. And that means a lot of code, and that means a lot of vulnerabilities. And that's exactly the case with RTF. The second most important feature of RTF files, it was created to be able to embed and render different types of objects. So you can include all e-objects in RTF files, which means images, fonts, annotations, flash files, which means, again, more vulnerabilities, more options to deliver exploits. As we can see, that's an example of some of the CVEs we were seeing lately with RTF files. If you are into threat intel, you know these are commonly used CVEs that was heavily used and implemented by different APT actors and cybercriminal groups. So in the next slides, we are going to focus more on feature and characteristics of RTF, which we can use to track and attribute RTF files. And to make it easier, we have grouped these features into 4 main groups, which we can map into the stages of Lord document or malicious document creation Michael have just explained, Lord document creation, payload selection, and weaponization. So these 4 groups or techniques are RTF metadata, obfuscation artifacts, and shellcode characteristics, and finally, RTF object characteristics and object dimensions.
So let's start with the simplest of those first, metadata author tag attribution for RTF files. Metadata tags within RTF files is the simplest because these are contained in the strings as plain text and in the properties of RTF files. These metadata tags are applied during the lore document creation prior to running the weaponizer script, which injects the malicious code to exploit vulnerabilities. What makes these such high-value IOCs is this is host artifact information taken from the weaponization environment, the threat actor's environment, and delivered to individuals at our organizations. It provides a high level of persona visibility and understanding. I include an example here that I like to refer to as Schrodinger's backslash. I've presented on it elsewhere. It's actually a metadata author tag and operator string used by a number of Chinese APT groups that when you pivot on it, allows you to identify multiple RTFs that can be attributed to different campaigns by Chinese APT groups like Goblin Panda, APT-10, and the Sun Orcal Reaver group.
Perfect. So metadata, as Michael just explained, is an easy way to be able to track and attribute RTF files. It provides visibility onto the operator level, where you see more artifacts of who is creating the lore document. A more complex way of tracking RTF files is shellcode attributes or shellcode attribution. As we know, shellcode is the code executed after we are successfully able to exploit a vulnerability. And it's very common that we see threat actors using or developing their own custom shellcode. And this custom shellcode usually have unique characteristics, which we can use to track and attribute a shellcode to a certain actor. Actually, while these characteristics are not unique to RTF files, but what is very important with RTF files is that they are text files. So RTF are usually ASCII characters, which means they are not using compression, they are not using any packing, they are not binary files like Office documents. So it's much easier to be able to spot and find shellcode bytes into an RTF file and develop a very simple rule to detect and match against it. Some of the examples of the shellcode characteristic we usually see and use to track shellcode is shellcode bytes, which is actually the shellcode code itself. Like if you have a unique code for the shellcode, you can easily write a signature to track and attribute it. The return-oriented programming get-kits, if an actor is using a custom get-kit in his return-oriented to pivot over data execution prevention, these addresses can be used as a good signature to detect and attribute and exploit to previously seen actor. Egg hunting tags, so while it's not very common in RTF files, but sometimes you can see the magic number or the magic string used in egg hunting can be very unique and can be used to attribute a shellcode. Other characteristic, which is more into the behavior of a shellcode, is dropped file names, like the very popular A.T files people were speaking about yesterday, that can be very effective into attributing a shellcode. Payload execution, are they using HTA to execute the script that's executing a file? Are they manually loading a DLL into memory and executing it? Are they using PowerShell to execute next stage payload? These can all be used as a characteristic to attribute a file. That's a very simple example of like a very simple rule you can develop to detect or attribute a shellcode found in files. The string here is for very special character use for the buffer overflow for CVE 2018-0798. Another example would be there's also simple rule that's used to detect the A.T, very popular Chinese actor shellcode. So just looking for an object inside an RTF file with the name of A.T. As we said, like shellcode might be a little bit complex because you might need a little bit of reverse engineering to be able to spot the shellcode and write a rule for it. But it's very persistent. Like actually, we see actors reusing their old shellcodes when they are moving to new exploits. And even in some cases, we have seen them using old shellcodes with 0 days. So if you are able to develop a good rule to detect shellcodes and attribute them, you might be able to do a very good hunting into shellcodes. So the next technique we are going to discuss are RTF obfuscation artifacts. As we said, RTF specification was designed to be very flexible. And flexibility meant complex parsers. And that doesn't only result into a lot of exploits, that also results into a different implementation of the RTF specification. And that means when you are developing an AV parser or an analysis tool parser, it's very difficult to implement all the options. And actually, actors usually make use of this by when you are developing an exploit that's targeting a certain parser, you can make use of this by inserting some obfuscation artifacts that might make it difficult for an AV to extract the payload. So how things works in RTF is that we have an object header and then we have an object data. And usually the shellcode or the payload or the malicious payload are in the object data. So actors are always trying to insert the obfuscation strings into the payload to make it more difficult to parse and extract the final payload. These obfuscation artifacts or strings are usually or sometimes unique to the actor who have been developing it and can be used to track and, again, attribute an RTF file to these actors. Again, so there is a lot of options and techniques that can be used for RTF obfuscation. It's out of the scope to be discussing them and explaining them, but there's already a lot of good write-ups on the internet explaining RTF obfuscation and how they work. We are just going to give a small or quick examples of how they look like and how we can use them in our Yara signatures. So as we said, we can see that there is an object here defined, and the object have a header, and the object have an object data. The object data, as we said, is the payload that contains the malicious data the actors are going to use to exploit the vulnerability. And we can see here actors can make use of the flexibility of RTF files. So for example, like you can define an object inside the data, and this object can be invalid characters, and still RTF parsers will be able to parse it in the right way. You can use different character encoding techniques. You can use white spaces. You can use new character lines. And still, the RTF file will be valid. But for AV scanners or for analysis tool, it will be very challenging to extract the payload. So an example of IR rule that we can use to detect this is, again, very simple. You just detect the obfuscation strings, which are unique, as we said. You have them in IR rule. And you look for this inside any RTF file, and you can easily attribute it to the same actor. OK, so the last technique we are going to discuss today, and the one which we have been using and have been proven to be very flexible, is RTF object dimensions and object characteristics. As we said, like RTF files can embed different type of objects. Some of these objects might have graphical representation. And as per RTF specification, when you have an object with graphical representation, you need to define the object dimension in the object header. This table is from RTF specification, and we can see you can define properties like object height, object width, object scaling, dimensions, and location. So the main idea here is when you are developing an exploit, these dimensions and these graphical representation properties are developed or generated during the exploit developing process. And usually they are very unique and they are very persistent. That means when you develop an exploit and then you have it hard-coded inside the weaponizer, it's very rare to have this changed. So actors might find that they need to update the shellcode. They will update the shellcode, but they will not play with the object dimensions. That's how object dimensions look inside an RTF file. So again, we have an object definition in here, and then we can see that in the object header, we have defined an object width 811, an object header 310, and that's the dimension of the object. And again, this is usually very unique. And this is how it looks inside the file. These are two different phishing documents from two different actors. They are both using equation editor vulnerabilities, and we can see the boxes in here, which represent the equation editor object. And again, it has a graphical representation, and these two boxes have the exact dimensions, which defines the same developer of the exploit. So as we said, this technique is very persistent. We have been using a signature for the well-known railroad weaponizer for more than 1 year. It was very successful. We have nearly catch all the samples used by the actors using the weaponizers. We have never seen a false positive in it. And we have implemented this technique with, as we said, different weaponizers, at least 22 weaponizers we are currently tracking. And again, if you look here, that's one of the railroad weaponizer files that was submitted to VT. After 1 year of using the exploit, it had a very low AV detection. Actually, one AV was detecting it, but still, it had the same string. If you look at the strings from VT, object dimension, the same object dimension we used to track the RTF file. So again, it's a very successful technique. AVs rarely use it for detection, which means actors rarely need to change it. So that's very persistent, and you can depend on it to track an RTF file.
OK. So that was a very thorough and very good coverage of these RTF attribution techniques. Let's quickly compare and contrast them to understand strengths and weaknesses. So the metadata is perhaps the simplest method that we presented. It's easy to track and provides a level of persona operator visibility. However, these are very impermanent, and not all metadata author tags are unique to a file. Windows user shows up in a lot of places. Shellcode is more permanent, probably the most permanent that we talked about, and can be very unique to the actor. But there is a sophistication boundary for analysts to be able to track these and make appropriate comparisons across campaigns, so technically challenging to do shellcode attribution. Obfuscation, on the other hand, like metadata, is easy to track. It's plain text in the strings of an RTF file, and it provides supply chain visibility, meaning if you're seeing different obfuscation gadgets used in different campaigns, you're able to understand the adoption of that obfuscation gadget across the threat landscape, and therefore the weaponizer. However, these are impermanent as well. Actors are often changing these obfuscation gadgets to frustrate static AV detection. And then finally, the object dimensions we believe to be very, very efficient. They are more permanent than either metadata or obfuscation. They provide the same supply chain visibility as obfuscation, and they can often be very unique to an actor. So let's visualize that quickly. We map these from the most fleeting to the most permanent, and then operator visibility to supply chain visibility. Metadata is the most fleeting with the most persona visibility, operator visibility. The encoding schema is the next less permanent. That's the obfuscation gadgets. That provides a decent level of supply chain visibility. Moving to the more permanent now, object dimensions are more permanent and provide probably the highest level of supply chain visibility. And then finally, shellcode is the most permanent, providing a low level of operator visibility. So at the beginning, we promised we were going to do an APT use case. Here it is, the Royal Road RTF weaponizer. This was a toolkit introduced in late 2017, coinciding with the publication of CVE 2017-11882. It remained in use through the middle of 2019. It was utilized by 5 different Chinese APT groups and 1 Indian APT group very briefly. It eventually made its way into the crimeware landscape, and you can find it delivering async rat today, probably in many of your organizations. So it exploits 3 distinct CVEs from Microsoft Equation Editor, which I'll cover, and it's identifiable by these unique object dimensions: object width 2180, object height 300. So like I said, the Royal Road Weaponizer exploits equation editor vulnerabilities. For anyone not familiar with the equation editor, it's a tool in the Microsoft Office suite that allows you to write complex equations. It actually was a feature that has been in the Office suite for many, many years, and it was acquired by Microsoft rather than having them write the code themselves and maintain the code base. That ended up being problematic in November 2017 when CVE 2017-11882 was disclosed. Because they didn't maintain the initial code base and they acquired it, they were forced to release an ad hoc patch binary for the equation editor. The result of that was it exposed additional vulnerabilities in the equation editor, CVE 2018-0802, and then later CVE 2018-0798. 0802 was exploited in the wild almost immediately following the patch in January. So despite being patched, the equation editor exploits, including the Royal Road builder, exploits equation editor vulnerabilities. I'm sure we're seeing these every day. So let me talk very briefly about the constancy of object dimensions. We found 5 different versions of the Royal Road Weaponizer in use in the wild. They're identifiable by their unique obfuscation gadgets. So all 5 versions had different obfuscation gadgets that they utilized. They targeted 3 different CVEs, those equation editor vulnerabilities I just mentioned. However, despite the varying obfuscation gadgets they utilized and the different vulnerabilities targeted, all of the object dimensions remain constant through these versions. So this is, again, the technique that we believe most successful for identifying different versions. One thing I do want to say is in our attribution process, we did not rely only on these object dimensions. We utilized metadata to be able to determine different operating areas between APTs from Mongolia or Central Asia. We used characteristics of shell codes and payload dropper methods to discern 8.T Chinese groups from the HTA methods utilized by Indian APT groups. So we really utilized all of the 4 methods across this presentation to attribute and identify the different APT samples that this research was based on.
Okay, so the Royal Road Weaponizer and CVE 2018-0798, that's a very good story that shows how persistent Chinese actors are, or whoever is behind the Royal Road Weaponizer. So as Michael said, like 1 week after the batch for 2017, 11882 was released, they started developing, or they released the Royal Road Weaponizer version 1. And then after the 0802 was discovered and a patch was released for it, they developed version 2, which was basically exploiting the new vulnerability. And then from 1 year, we have been seeing a lot of samples submitted to VT, exploiting both vulnerabilities, until I think the early 2019, we started seeing some Royal Road Weaponizer samples submitted to VT with very low detection, and our scripts were not able to attribute it to either of the 2 exploits. So we started doing static analysis, and we figured out that they are using a new exploit. And we were not able to attribute it to a certain CVE because we didn't find more information on it. And we had to reach for our colleagues on Microsoft for help. And they said, OK, that's CVE 2018-0798. And that was very strange. Why would they invest time into developing a new exploit if a new patch is already working for them? And we figured out that for the actors, when you use the exploit 11882, it only works with old version of equation editor, while 0802 works only with new or the patched one after the 1182 patch. So when they are exploiting a target, they have a 50-50 probability of a successful exploitation. So they were working for 1 year into finding a new CVE, which is a little bit different, because with both old CVEs, they were vulnerabilities in how equation editor were parsing the font string name, while this one was in the matrix record parsing. And for this vulnerability, it works in all known version of equation editor, which means higher success rate. And that, again, shows how persistent they are and how hard they are working to make higher success rates.
Okay, so now that we've covered a lot of the technical methodologies and the attribution methods, let's talk about the groups that were actually using these. From beginning in November 2017 to May 2019, we saw the 5 different versions of Royal Road in the wild. Beginning 5 days after the disclosure of CVE 2017-11882, the group believed to be aligned with the Chinese state, referred to as APT 40, Leviathan, also Temp Periscope, started using a version 1 that exploited CVE 2017-11882. Shortly after that time, another group believed to be associated with the Chinese state, primarily targeting Vietnam, Conimes and Goblin Panda, began utilizing that same version 1 of Royal Road, identifiable by the obfuscation gadgets. Shortly after, in January, we saw a new group, a group that some refer to as Temp Trident, that are known in different areas for their use of the Ice Fog payload. Ashley Shen from FireEye has done some great work tracking the different Ice Fog clusters. We saw them adopting a Royal Road version 2 that had different obfuscation strings. Goblin Panda shortly jumped on that version 2. Then something interesting happened. In spring of 2018, for a very short amount of time, we saw 2 to 3 samples by a group that is known as Sidewinder, associated with the Indian state interests, primarily targeting Pakistani defense and military. We're not exactly sure how they got their hands on version 3. It is a very similar version to version 2, just with a slightly different obfuscation gadget, still exploiting 11882. So it's possible it's a fourth-party collection situation. We've also broached the possibility that there is a shared supplier of these builders selling to multiple APT groups. But anyways, after that point in time, we see version 4 enter the landscape. This is when CVE 2018-0802 enters the picture. A group called Reaver, or Sun or Cal, reported by Silence, started utilizing this in spring of 2018. Then we see Goblin Panda and Temp Trident also jump on the version 4 for quite a while. And then finally, version 5, the 0798 that Ghareeb explained, they're adopting new methods to avoid detection. We see a group known as Goblin Panda use it first. Then another APT that primarily targets Mongolian geographies, referred to as Temp Hex or TA428, using a COT-X rat malware payload. And then finally, Temp Trident adopts Royal Road version 5. One thing that I do want to state, and there have been other talks here on the Belt and Road Initiative, the areas of operations for these groups are mapped on here with blue triangles. We believe that it is not insignificant that all of the areas of operations, as well as some of the themes, are usually economically motivated and have some sort of relevance to one of the operating areas of the Belt and Road Initiative. So the correlation between the Belt and Road Initiative and the Royal Road RTF weaponizer is significant.
So the Royal Road weaponizer usage timeline Michael have explained was a very good example of what we called weaponizer life cycle. So the 2 scenarios we have for the Royal Road weaponizer was that possibly the Chinese actor have exploit developing capabilities, and they were able to develop the weaponizer, and then they handle it first to the most sophisticated Chinese actor, or the actor who have the more prioritized objective to the Chinese operators. This actor used it exclusively for a couple of months until they have version 2 of the exploit. Then version 1 was given to the least important actors, who started using it, and then the most sophisticated got version 2, and then when they got version 3, version 1 got being given to an Indian actor or sold to an Indian actor, which we have seen using it twice, and then the cycle goes on. When they have a new version, the old version is being sold out to commodity malware or cyber criminal, and that's an important point where we always say we are worried about cyber weapons and exploit developed by state-sponsored attacks ending out being used by cyber criminals and commodity malware. And then the cycle goes on. Whenever they have a new version, the more sophisticated get the new version, the old one is handled to the less sophisticated, and the old one is sold to other actors. To summarize the lessons we learned from tracking the Royal Road weaponizer, as we said in the beginning, it's very useful to be able to track and attribute weaponizers. It gives you higher visibility on the actors, what are their supply chain, what are the connection between them. Being able to track Royal Road weaponizer, we find connection between different Chinese actors. We find possible connection in supply chain between Indian and Chinese actor, and we figured out that how they work and how they are improving their exploits and trying to find new ways for more success rates. I think that's it, and we are out of time, so if you have any questions.